Another type of diagram, most useful to visualize the stability of different oxidation states of an element, is a Frost diagram or Frost-Ellsworth diagram. This type of diagram gives a more graphical description of a given system. Latimer diagrams are sometimes confusing due to the lack of additivity of the potentials. If you remember what we have already discussed about the Latimer diagram, you will know that if we need to calculate the whole potential of two successive redox processes, that potential will not be the sum of the both potential of the both process, but it will be a weighted average of them. However, the Frost diagram avoids that limitation and gives us a more graphical description of a given system. Let's see what this diagram is about and how we can construct it. We know that when a particular species undergoes a redox reaction, there is a change in free energy that is proportional to the standard reduction potential through the following equation, where F is the Faraday constant and N is the number of exchange electrons in the redox reaction. Although that gives us the free energy change in joules, and in this type of diagrams the free energy change is usually expressed in electron volts rather than kilojoules per mole. In that way, for one electron process, the difference between two energy levels gives us directly the oxidation or reduction potential. In order to obtain free energy in electron volt as unit, we divide both sides of the equation by the Faraday constant to give the following relationship. By plotting this energy change on the y-axis versus the oxidation state of the element in the x-axis, we obtain a plot that is known as a free energy oxidation diagram, or more precisely, Frost diagram, in honor to Arthur A. Frost, who designed the diagram in 1951. That representation will indicate us the stability of a particular oxidation state of an element. Since the lowest the value of the free energy, the greater its stability. In other words, the most stable state of an element corresponds to a species that lie lowest in the Frost diagram. The values of free energy change in the ordinates are scaled in integers, with values above and below 0, whilst oxidation states are scaled in abscissas as positive and negative integers, usually in increasing order, although it can be also shown in the reverse way. We start to construct our Frost diagram by taking a value 0 for the Gibbs free energy, for the uncombined element, which also have an oxidation number of 0. Therefore, the point 0, 0 will be our starting point, and we begin to build it up stepwise the rest of the diagram, from here taking a redox couple at a time. The values on the ordinate axis can be obtained directly if we consider the oxidation number chain with respect to the pure element. In that case, the value will be the multiplication of the number of electrons transferred during that chain by its standard reduction potential. Finally, if we connect a species of adjacent oxidation state bad lines, that will give us a qualitative view of the redox properties of the element in its different oxidation states. In order to examine this important feature of Frost diagrams and learn the way to construct them, let's do some example. Let's examine the construction of the Frost diagram of oxygen from data obtained from its Latimer diagram in an acid solution. As we discussed, the first point of the Frost diagram will be the 0, 0 point, corresponding to the standard state of oxygen, that in this case is the dioxygen molecule, where the oxidation state of the element obviously is 0. Now, if we consider the change in free energy for an atom of oxygen, we will have the following equation. Accordingly, for the first reaction, reduction of oxygen to hydrogen peroxide, we have the point -1 in the abscissas, corresponding to the oxidation state -1 of hydrogen peroxide, whilst the ordinate value will be -0.68, as a result of multiplying the standard redox potential, 0.68, by the number of exchange electrons, 1 in this case, and finally multiply by -1. The following point of the diagram will be the point for water, -2, -2.46, corresponding to an oxidation number for water of -2 and the result of multiplying the number of exchange electrons, 2 for that reaction, with the electrode reduction potential. Alternatively, this point can be obtained by employing the electrode reduction potential of the reduction of hydrogen peroxide to water. In that case, the number of exchange electrons is 1, that multiplied by the potential, 1.78, and changing the sign gives us minus 1.78. That is, the point will be 1.78 units below the previous point, therefore minus 2.46 units below the origin. As we have discussed, the Frost diagram can be easily interpreted in order to obtain very useful qualitative information about the oxidation state of a particular element. First, it's important to remember that although we have represented the diagram with oxidation state in the x-axis on increases order, and we will follow that convention during this course, you can find similar diagrams in the literature on the contrary way. That is, decreasing the oxidation states from left to right. If we expansion the diagram of oxygen, we can deduce the following aspect. The steeper the line joining 2 points in the diagram, the higher the potential of reduction of the corresponding couple. That prediction is based on the fact that the slope of the line joining 2 adjacent points is equal to the reduction potential. We can see this fact in the oxygen diagram, where the line connecting hydrogen peroxide and water is steeper than the line connecting oxygen and hydrogen peroxide, according with the reduction potential. The species more thermodynamically stable will be found lower in the diagram. In our case, water, which is placed in the lowest point of the diagram, must be the more thermodynamically stable species. According to our convention, species that are high on the right of the diagram will be strongly oxidizing, while those species high on the left will be strongly reducing. We can also do other prediction when we consider a reaction involving 2 couples. If the point of a species lies above the line connecting the 2 adjacent species, we can deduce that this combination will be unstable with respect to its disproportionation. For example, in our oxygen diagram, hydrogen peroxide is in such condition. Contrarily, if the value sits below the line joining the species with oxidation number on either side of it, those species will be likely to undergo comproportionation to this lower value. Therefore, the Frost diagram allows us to interpret qualitatively in a relatively easy way the main features of the different oxidation states of a particular element. But this interpretation has the drawback that we are comparing free energy data from standard condition, that is, 1 molar solution at pH of 0. But for other concentration, the relativity stabilities of the different species could be different. As the pH changes, the potential of the reduction of a half reaction that includes the hydrogen ion will also change, and even more important, the species themselves will change. This fact can be easily observed in the Frost diagram of manganese in both basic and acid pH. In a basic media, manganese 2 ion doesn't exist because insoluble manganese 2 hydroxide is formed. It's for that this is the species that appears in the diagram in this condition. We can see, for example, how manganese dioxide is more stable in basic than in acid condition, or the different reducing strength of manganese metal depending on the pH. Finally, it is important to know that the Frost diagram displays information about the thermodynamic function, but it doesn't contain any information about the rate of decomposition of a particular unstable species. This aspect is very clear in the reduction of permanganate to a lower oxidation state, which is thermodynamically favored but is kinetically not favored unless there will be in presence of a catalyst.